Welcome back. This is Fundamentals of Micro and Nanofabrication. I'm Swayam Prabha from IIT Bangalore, and this will be the concluding lecture on the module of additive processing and physical vapor deposition. We shall finish the discussion on metallization. So, the last lecture we looked at that the fact that there are multiple metal layers in silicon, that when we are making contact with metal and silicon, we have to discuss some details such as the contact resistance, the formation of silicide, and those details affect the recipe and the temperature at which the substrate can be taken to. Typically, after metals, you do not heat up the substrate because of these issues, but if you do have to, then you must select the appropriate metal and the appropriate temperature. In this lecture, we shall discuss another very important problem with metals, which is electromigration, and then we will transition to other one more issue, which is diffusion and use of barrier layers. Right. So, let us get started. So, what is electromigration? So, supposing you take a metal line in a fabricated device. So, this is what you are looking at. So, there is no silicon here. This is simply a metal line that is sitting on silicon, that is sitting on silicon, and you are taking a top image. Supposing on the right hand side of this device is a positive voltage and the left hand side is grounded. So, the current is flowing from right side to left hand side. Because of the dimensions of these metal lines in microfabrication tends to be small, and also metal tends to be very conductive, the current densities can be fairly high. So, in this case assume it is around 10 power 5 amps per centimeter square. So, the density is high, but if you do the calculation of a cross section of an actual metal line, the actual amount of current is maybe 1 amps or so. Right. So, if you keep flowing this current for a long time, what people have noticed is that with aging, the metal lines start to degrade. So, if you look at this figure again, you will actually see that this is the aged figure. So, initially it was a nice smooth line, but now it suddenly starts showing voids, right, and it starts showing some helix and protrusions. And it almost seems like what happens is that the aluminum migrates from these void regions into these regions to form the hillock. So, there is some sort of a mass transport happening, that as the current is flowing from right to left, the aluminum seems to be flowing from left to right at a very slow rate. And the other observation was that this problem seems to become worse as the line becomes thinner, which obviously was happening as the devices were being scaled due to Moore's law. So, this was a huge problem for reliability, because even though your silicon is very reliable and the devices are very good in complicated circuits, with time the metal lines would degrade, the delay of the line would increase, or they would just fail, which would mean the devices would fail. So, this is the issue, right. So, the issue is aluminum is moving. Now, when aluminum is moving, the first step that the first thinking that people, the first thought that came to people was that clearly this aluminum is diffusing. Well, diffusing by what mechanism? And the way to analyze that could be to compare the diffusivity that they are observing to the known diffusivity of aluminum through some of the known mechanisms. So, people had measured diffusion of bulk aluminum in aluminum, right. This is not silicon, this is aluminum diffusing in the line itself. So, there is a bulk diffusion of aluminum in aluminum, and turns out the activation energy for that process is 1.4. Aluminum can diffuse on the surface, the activation energy for that was 0.28. The grain boundaries, so remember these are not single crystalline aluminum, right, these are polycrystalline films, because we are just depositing them through some physical vapor deposition process. So, the grain boundary mediated diffusion has a activation energy of 0.4, 0.5, and in some cases the grain boundary and the bulk diffusions combine to give you some two dimensional features which have an activation energy of around 0.6. So, what people were able to show was that what is actually happening in this film is that you have grains, right, and these grains are of random orientation, because in physical vapor deposition we are not necessarily trying to grow an oriented metal film, we are just doing an evaporation. And what is happening is that as the current flows from right to left, the electrons flow from left to right, and it is that flow of electrons, just the sheer number or momentum of the electron, that pushes on these grain boundaries, and by pushing on these grain boundary moves the material out of the way, and that is what ends up causing this electromigration. Right. So, just empirically, just comparing these barriers, the activation energy, they were able to actually conclude that this is the sort of mechanism that is happening. So, the measured for electromigration, the measured values were around 0.5, 0.6, and because those values match with the grain boundary and the grain boundary plus bulk diffusion, those are the mechanisms that are probably causing this. Okay. Now, another interesting piece of insight came from very interesting but probably serendipitous or lucky discovery, is that the electromigration changes if you change with very small amounts of impurities in the metal. So, in this case, it's a little complicated slide, so please bear with me. So, what we are looking at is failure time. So, assume that if there is electromigration, ultimately the device will fail, right. So, what is the time before the device fails? If the electromigration is really bad, the failure time will be really small, and ideally speaking, you want the failure time to be as large as possible, which means the electromigration is as low as possible, correct. So, good is in this direction. So, you want to go up. Now, the x axis is cumulative failure percentage. Now, you see this is a stochastic process. It can happen at a certain rate, but different lines would have different thicknesses, so it would affect different lines differently. So, there would be a cumulative failure. So, so what you have to do is say you have to measure 100 devices or 1000 devices. So, some devices would fail early, some devices would fail late. So, you would have these statistics. So, at some point, so for any, what you would do is you would test 1000 devices and you would plot at what point they failed, and you can then plot a cumulative figure, right. So, you would start seeing failure at some time, and then as more and more devices failed, you would accumulate the failure rates and ultimately reach 1. And so, what this curve is trying to tell you is the rate at which the migration is occurring. So, everything would be monotonically, any curve would be monotonically increasing in this graph, but if you have for a given cumulative failure, say if the time it takes for 50% of the devices to fail, if your failure time is larger, then that means your electromigration problem is less. So, for the same cumulative rate, if your failure time to failure is higher, it is better. Okay. All right. So, with that, let us analyze the data. So, what they found was with 100% aluminum, you actually had some amount of migration. This is your base case or control case. As you added a little bit of copper, the failure time increased, which basically means the device took longer to fail. So, 50% of the devices took longer to fail. If you add up to 4%, it takes even longer to fail. So, this is more migration, that is less migration. So, clearly if you were to make a contact, or you were to make not a contact but a metal line, it is better to make it with 96% aluminum and 4% copper than it is to make with 100% copper, 100% aluminum. And the reason for this is the addition of impurities tend to slow down the self diffusion. So, a lot of this movement is because aluminum is diffusing in aluminum. If aluminum has to now diffuse into a copper aluminum matrix, the diffusion is a little bit slower. Now, the canonical story that I have heard, I do not know if it is true or not, is the reason the author actually was able to see the copper is that he was using E-beam, and the E-beam was slightly misaligned, and so the electron beam was not just falling on the aluminum crucible, but also a little bit of falling on the hearth, which is made of copper. So, that allowed them to get a little bit of copper into their system, and then they saw much lower electromigration rates. I do not know if that is a true story, but it is an interesting story nevertheless. All right, moving on. The second thing that people saw they could do to improve reduce the problem of electromigration and improve their reliability is to use higher melting point metals. So, if you look at the activation energy for migration on the y-axis and you plot it versus melting point of a certain metal. So, this is tin, a very low melting point metal, aluminum is a little higher. If from aluminum you go to something like cobalt, which has a higher melting point, it tends to have even a higher activation energy for migration. So, if you were to convert all your aluminum lines to cobalt lines, there you can probably make them more reliable. Of course, cobalt has much higher resistivity, so the resistance of your lines will be a little worse, but if you can live with that optimization for higher reliability, maybe that is something to be done. Also very interesting is if you look at some of these silicides which are plotted up there. So, platinum silicide, tungsten silicide, molybdenum, tantalum silicide and tungsten silicide, they also tend to be very high melting materials, as we discussed in the table before, I think in the previous lecture. So, these silicides are actually much better for conductivity or for reliability, not for conductivity, for reliability, because they have much higher activation energies for migration. So, in devices where reliability is more important, say in military grade, satellite grade devices, people often moved away from metals such as aluminum into metals such as either into silicides or to metals such as tungsten, cobalt, which tend to have higher melting point. Now, let us have a discussion on how do you actually prevent electromigration, supposing you cannot get away from aluminum. So, you have the same aluminum and that aluminum is diffusing. Is there anything we can do from a morphological standpoint to actually prevent the problem? So, the answer is yes, and we shall discuss what we can do with under two cases. So, the first case we shall talk about is what happens when we change the grain size. And the second second thing that we will discuss is about how we can change the geometry. So, first we shall discuss how grain size or morphology affects things, and second we will discuss how geometry or width of the line affects things. So, first take grain size. Now, let us take two cases. So, what you are looking at is the top view. So, you have a metal line. So, here is a metal line and you have zoomed in, so you can actually see some grains. So, this is some random grains that I am representing with hexagons and triangles. And say the current is flowing from right to left, which means that each of these grain is seeing a force from the electron flux that is going from left to right. Now, compare this random grain orientation to a case where the grains are very large. So, the grains are large or the grains are columnar, then what you will actually see from looking from the top is just flat grain boundary. So, this grain is essentially so large that the only grain boundary that you are seeing is one that is at 90 degrees to the current flow. Okay. So, what would be the effect? And to understand that, first let us do an apples to apples comparison. So, let us assume that the width of this metal line, which is this dimension, is exactly the same in the two cases. So, the only thing we are actually changing is the grain size. So, when we do that, now let us see what is happening. Let us do a thought experiment. So, the force is being applied on these grains from left hand side as the electron flux falls on them. Now, if the grains are small or they have these angles, some component of this force would be applied in the direction left to right, but some force would also get induced into the vertical direction. So, there will be some cos theta component. So, some component of the force is now acting on the vertical directions, which is these two red lines. What this force does, it moves these grains out of the way. It pushes the grains out of the way, and that is electromigration that leads to an open circuit, and that is a problem. If you compare this random case with the case where you have a columnar or large grain structure, once again you have the same force. However, now that force is being applied on essentially a vertical boundary. If there is a vertical boundary, there is no cos theta component. There is no cos theta component that can push this grain in the vertical direction. So, there is no force, there is no vertical force on this grain, the only force is in the left and right direction, and that means that this grain cannot move, because this grain is bounded by this grain. So, it cannot move left to right because this grain cannot move left to right. If you really want an image in your head, imagine there is a straight line of people standing, and if you force those people to always stand in a straight line and you push the person at the back, everybody will feel compression, but nobody would feel a cos theta force that pushes them out of the line. Right? However, if now all of those people are standing at a slightly different angle and I push people from behind, somebody might see a cos theta component that will push them out of the line. So, that is what is happening. So, what is the net effect on electromigration? So, once again, if you plot the mean time to failure, how long it takes for a device to fail, once again, longer the time, better the device, lower the electromigration. So, then that has a dependence on grain size. For small random grains, the mean time to failure is low because the electromigration problem is larger. For large columnar grains, the mean time to failure is large, electromigration problem is smaller. So, this is where you would like to be. Now to ask the question, how do we actually change the grain size of a metal film? I urge you to go and look back at the previous lectures on deposition, where we discussed how changing in substrate temperature, changing the arrival energy of ions, changing the argon bombardment, changing the pressure of sputtering, you can actually change the morphology and get larger grain films. So all of those techniques can now be applied to actually reduce the problem of electromigration. Let us now discuss the effect of geometry. To keep apples to apples comparison, let us keep the grain size constant. So let's say that they all have the same randomized grains. So a wider line that is thicker would actually have a lot of grains. A thinner line would actually have very few grains. Now, when you apply the force from the left hand side due to electron flow, even if some of the grains were to move out of the way due to electromigration in the thick film, it would not change the characteristics too much, simply because there is too much redundancy in the system. There are so many grains that there is always some other grain to compensate. However, for the very thin line, some of these grains are critical. If, for example, this grain moves out of the way, then that line becomes open circuited. So if you were to plot the mean time to failure as a function of line width, for thicker films there is a lot of redundancy. So the electromigration problem is less, the mean time to failure is high. However, for smaller line width, the mean time to failure can be fairly small, because one critical grain, if it ever moves out, your device will become open circuited and fail. If you combine both of these effects in one graph, oh, my animation is a little off, it actually looks something like this. So if you were to plot the mean time to failure as a function of line width normalized with grain size. So we are plotting this, the fraction of line width by grain size. This tells you how large your line width is compared to the grain size. Okay. So if you were to plot that, you would actually see that you would actually see a U-shaped curve. You actually have higher reliability or longer mean time to failure for cases where the line width to grain size ratio is very large, which means that either the grain sizes are very small or the line width is very thick. You would also get high reliability for the case where the line width to grain size ratio is very small, which means either the line width is very small or the grain size is very large. However, somewhere in the middle, often if this ratio is around 3, you actually have the worst of both worlds. Neither do you have enough redundancy to work around electromigration, neither do you have small enough neither do you have large enough grains to actually prevent electromigration. So your reliability is actually the least somewhere in the middle. Okay. So this is the region that you would like to avoid. This is the most defect prone or the least reliable case. You always want to tune the morphology, so either you have redundant pathways or you have a columnar looking structure. Okay. So this is the take home message. So this is how you can tune geometry or grain size or deposition. Something has to be tuned such that you get better reliability. Another thing that people do is to use higher melting point metals as barriers. So supposing you had that aluminum line, if it has no voids, which is at the start of the its functioning, everything is good, the current flows. With time you would accumulate a void where no current flows, and that is bad, the device fails. Now you can replace all of aluminum with titanium, but titanium has much higher resistivity, would make your device which would increase your ohmic losses and make the device slower. A common fix to that is to divide and conquer. Not just have aluminum, but also have titanium buttering it, right? So you have titanium on the back and top. Supposing aluminum migration does happen and you are to create a hillock in a void in aluminum, the current can still flow. The device will not fail because the current can now go through the titanium and out there. This much transport in titanium would probably not significantly change your resistance, so not change any of your delays, but make sure the device doesn't fail. And titanium on its own will probably not suffer electromigration so much because it's a high melting point material. So you have sort of used both the materials to their advantage and solve the problem of electromigration. So this is called cladding, and cladding is often used to reduce this problem also. You can also solve the problem of electromigration by just having some redundancy in the system. Here is an example how. So supposing you had two different metal layers. So this is in this case people are using copper, but similar arguments can be made with aluminum. So, you have copper, the two of them are connected with the via. So, this is say M2 and this is M3. So, two different levels of metals that are connected through a via, and everywhere else is silicon dioxide. And the current flows from top to bottom. So, as the current goes from top to bottom, the electrons flow from bottom to top, which creates pressure on this copper and it does electromigration. So, you create a void here. Right? And as more and more current flows or as time goes by, this void will keep becoming bigger and bigger, and you will see a creeping increase in your resistance. A better design that circumvents this problem without changing anything is it creates a reservoir. So, when you are trying to create a connection between the top copper and the bottom copper, you can always overdo it and create this extra layer of copper, which prima facie does not do anything to improve resistance, but it solves the problem of electromigration. Because now when the current flows, there is always this reservoir where the voids can be, and even if you create a void here in the critical path of current flow, you are actually not changing the resistance too much. So, with time, the change in resistance that you observe here will actually be much less than the change in resistance that you actually observe here, which is solving this problem by just superior design or more robust design. After electromigration, another very important aspect to discuss is the industry's movement to copper from aluminum. So, aluminum has great things going for it. It's low cost, it can be deposited through several different techniques fairly easily. It forms very good, relatively good contacts with silicon. Due to anneal, it creates great interfaces. It has very low resistivity, I think the third or the fourth lowest in the whole periodic table. All of these is great. However, aluminum suffers through electromigration, and as devices kept becoming smaller and smaller, even aluminum's resistivity reached its limit, and the device speed was decided by the delay in the metal line. So, the only way forward was to increase the resistivity, which meant a movement from aluminum to copper, which has a very high conductivity. Now, one of the challenges with copper is a very potent defect in silicon. Any diffusion of copper into silicon would actually kill your device performance very easily. That is not the case with aluminum. So, while there was this pressure to go from from aluminum to copper, but there was also this counter pressure to not use copper because copper would make your device worse. So, somebody had to figure this issue out. Now, how do we solve this problem of copper diffusion? Is through the use of barrier layers, specifically titanium nitride. The most popular implementation of that in a commercial device is called a Damascene process, and of course, the details are much more complicated, but in a very simple way I will try to highlight what the process tries to do. So, supposing you have a silicon layer and you are trying to make contact to it, and assume there is a device here that I am not showing. You have some silicon dioxide in which you have cut a hole, and this is your tungsten via. So, this till now everything is normal. After that, if you were to make a copper interconnect, what you would ideally do is you would simply deposit copper. But as we discussed, once you deposit that copper, and for where even at back of the end processing temperatures of 400 C or so, this copper will start to diffuse through the silicon dioxide layer, go to your silicon, kill your device. So, that is not acceptable. So, what people actually do in the Damascene process is they deposit a thin layer of titanium nitride. Now, titanium nitride is so dense and such a high temperature material that it does not allow too much diffusion. And the thickness of this titanium nitride is selected such that for the thermal budget, for the time and the temperature that you expect in the remaining part of this process, the copper would actually not be able to penetrate the titanium nitride to reach silicon dioxide and silicon, and that is how you protect it. And this titanium nitride is conductive, and it is conductive enough that this thin layer of titanium nitride between the copper and the tungsten would not significantly change your series resistance. So, till now it is good. So, what you have is you have a metal, you have a cladding, so this titanium nitride is a cladding. Then you do your patterning of copper just like you would do normally, and along the way you also pattern your titanium nitride. Then you do a conformal deposition of titanium nitride all around, right. So, now this is a cladding that is not just on the top, but also on the sides. So, all the fundamentals that we discussed on what will actually give you edge coverage and what will give you conformal depositions, under what conditions will you get conformal depositions, those apply. You need to be smart in your deposition chemistry and deposition process such that you actually deposit a nice uniform titanium nitride layer on the sides that is also of the correct thickness. Once you do that, then you deposit silicon dioxide. This is done even if there is in any other process which involves multiple metal layers, and then you do some lapping and polishing just to smoothen things out. So now what you actually have is you have a cross section of a copper that is going somewhere, but all around that copper is the titanium nitride deposition, and this cladding is what actually prevents from this copper from leaking out or diffusing out and preventing contamination, and this is what the Damascene process is. So with that, we'll end metallization and the discussion on metallization. I'll have a little bit of discussion and epilogue on something that is common to all deposition or all additive processings, and those are stiction coefficients and a little bit of discussion on energy, right. So let's get started. So if you look back at all the things we have done in additive processing, we started from diffusion, we did implantation, we did chemical vapor deposition, we did ELD, we did evaporation, we did sputtering. And if you go and look back at the details, you will realize that the energy of depositions in all these cases was slightly different. And that actually has a huge bearing on the sticking probability. So stiction coefficient or sticking probability is one thing that I have till now in all the lectures assumed to be 1. Practically that is not the case, it actually changes. But to what extent does it change and under what conditions will it change is the subject of the slide. So it turns out the sticking coefficient is 1 under 2 extreme cases. Case number 1, if the incoming atom or ion or any material is at very low energies. So if it is coming very gently, then the stiction coefficient will be 1. The second option, if it is coming with an extremely high energy, the stiction coefficient is 1. So what are the 2 extreme cases where this will occur for, among the techniques we have learnt? So evaporation, which is the most gentle, or maybe CVD, which is one of the most, the energy at which the material comes on the surface is essentially 0 simply because this is diffusion, right. There is almost no impact. So in that case, if the kinetic energy of the incoming atom is very, very small, the stiction coefficient is 1. There is almost no backscatter when CVD happens. Similarly, if you are doing ion implantation, where the energy was hundreds of kilo electron volts, so 10 power 5. So for 10 power 5 EV also, you would have a stiction coefficient very near 1 because it is just very small probability of something coming back. As you go towards ALD, where we looked at chemisorption, the energy is slightly higher, or if you start looking at evaporation, the energies are slightly higher, but still low enough that by and large the stiction coefficient is more than 0.9, so we assume whatever comes on the surface sticks. Once you start getting to a few EVs, 10 to 100 EV, that is where sputtering happens, and at those type of energies the stiction coefficient is actually the lowest. It can be as low as 0.2, 0.3, which basically means only 20% or 10% or 25% of the material, incoming material is actually sticking to the surface, rest all is getting backscattered. So, the sticking probability is least in sputtering, and that is why we had to take into account of this phenomena when we are trying to do when we are trying to model the deposition rates. Okay. Once you start increasing the energy again, you reach that implantation regime, and the sticking coefficient starts going back up again. We can talk about this whole phenomenon in terms of kinetic energy of the incoming atom or flux. We can also talk about this in terms of an effective temperature. So typically CVD ALD tends to happen at around 100 to 500 Kelvin. So that is what these ranges are. At higher temperatures or higher implant temperatures, which is what you have under plasma, the sticking coefficient becomes low, and at very, very high temperatures equivalent to what is there in an implantation system, which is 10 to the power 8 Kelvin or equivalent, the sticking coefficient again rises. Okay. Finally, a general discussion on, practically speaking, which types of techniques are used to deposit what. Now, there can always be exceptions. You can always deposit metals using CVD, but that is not primary goal. You can always deposit silicon using evaporation, but that is typically not done. So what is typically done? What is the first thing to try if you are trying to deposit metal? So if you are trying to deposit epitaxial silicon, I would suggest you start with APCVD or LPCVD, which gives you a relatively clean and perfect growth lattice matched silicon, right? Typically this needs to happen at temperatures that are high, so 1000, 1100 degrees C types. We can also do polysilicon. In this case the material is not epitaxial. You would lose in grain size and orientation, but you would gain in terms of temperature. You can actually deposit polysilicon at much lower temperatures. But I would still recommend depositing APCVD or LPCVD simply because the other than grain size, there is also an danger of having impurities, and those tend to be lower in LPCVD or APCVD methodologies. You might have to deposit insulators if you are trying to do silicon nitride. Commonly used things are LPCVD or plasma enhanced CVD. The difference between these two is just the temperature at which you do the deposition. If you are trying to do something for diffusion masking, maybe LPCVD and its high temperatures are okay, but if you are just trying to do some passivation or low temperature dielectric, you may want to use plasma enhanced CVD. Silicon dioxide, the highest quality is always gained by native oxidation, which we have discussed a lot, but that requires high temperatures. If you want to deposit things at lower temperatures, you might want to go to CVD or plasma enhanced CVD approaches. If you want to deposit things at silicon dioxide essentially room temperatures, you might have to look at ALD or sputtering. Okay, but these types of films tend to be only good for low cost dielectrics or as optical films. They are not necessarily very good insulators, they are not very good electronic films. If you want to deposit metals such as aluminum and aluminum alloys, you may want to deposit evaporation. You may want to use evaporation. However, for aluminum alloys, evaporation is not good because alloys in general cannot be evaporated, so you may want to use sputtering. These can often be deposited at much lower temperatures because high temperatures are not good for metals, they tend to diffuse. If you want to deposit tungsten for your VRs, you might want to do sputtering, though you can also do LPCVD if conformality is proving to be a challenge. The issue would be that CVD would require little higher temperatures. If you want a cladding layer or a barrier layer, titanium nitride is a good option. You can do it with reactive sputtering. You can also do it with MOCVD. If you want to do copper, you can do simple things like sputtering, but for sometimes you want very thick coppers. So, for example, you want a 1 micron or 2 micron or 5 micron thick layer of copper. In those cases, evaporation sputtering tend to be too wasteful. What people often use is electroplating, and that we had, I think, one slide on somewhere before. If you want to form a silicide or you want to deposit a silicide, you can simply deposit the titanium in this case. So, for titanium silicide, you deposit, just sputter the titanium and then do a reaction with silicon to form the silicide. And different silicides require different temperatures. Depending upon your thermal budget and your appetite for high temperatures, you may have to appropriately choose a metal and an appropriate silicide. So, with that, I think we have come to the end of this module. From now on, you will have a module on photolithography, and this ends both the sub module of physical vapor deposition and the larger module of additive processing. Thank you.